Hello everybody, this is week 9 and lecture number 1. I hope everybody is doing all right. So we're 9 weeks into the course, just about 3/4 of the way through. Next week will be reading week, so you have a chance to catch up, I hope, on things, and I hope you are staying abreast of the current progress and allocating time each day to review these lectures and do the work required. I guess I'll see you after the break. So today we're going to talk about, we're going to start in chapter 6. So last day we were talking about sampling distributions on the mean and the variance, and now we're going to use those distributions to talk about things like confidence intervals. And then in week 10, which is after the break, we'll talk about hypothesis tests. Okay, so with no further ado, we're going to start this lecture off by talking again about point estimates. We've seen the X bar several times now. That's the average or the sample mean. And as we mentioned in the last lecture, this is a point estimate of the true mean, mu of x. But it's an estimate. Every time we change our set of observations xi, we're going to get a new value of x bar, so x bar is a random variable. So the question is, if I tell you that x bar is 10, you don't know from that how good of an estimator x bar actually is. Is this close to the true mean, or is it far away from the true mean? Well, of course, that depends on how many samples we've taken. If we've only taken 3 samples, it's probably not a very good estimate of the mean. If we've taken 1,000,000 samples, it's probably a pretty good estimate of the mean. So one of the some of the things that we are interested in investigating for our estimators is how good they are from a variety of standpoints. First question we could ask is this estimator unbiased? In other words, is it aimed at the correct thing? What that means, if it's unbiased, it means that the expected value of the estimator is equal to the thing that we're trying to estimate. It is aimed at the proper thing. And in fact, we can substitute in, we know x bar is equal to 1 over n sum of the xi's, which is the 1 over n can come out front, and then we get the expectation of a sum, which of course is the sum of expectations. And I get 1 over n times mu x plus mu x plus mu x itself, n times, and the end result is just mu x. So that means the expected value of this estimator, x bar, is just equal to the true mean of the population, and therefore it's unbiased, and it does give us an estimate of the true population. We can think of all, x bar is one statistic. It has this form here, but a statistic is any function of our observations. So I could write down a new estimator, I'll call it x hat. I could write this as being 1/7 the sum of 3 random variables x1, x3, and x7. Well, of course, we see automatically this is a terrible estimator. If we're trying to estimate the mean, this is just not going to work. For example, its mean, expected value of x bar, is 3/7 times the mean of x. So it's not at all aimed at the true mean. In fact, it's about a little less than half the true mean. Also, it obviously doesn't use all the information. I'm missing x2, x4, 5, 6 as well. So it's, again, not a good estimator in that point of view. Some other things about estimators are they efficient, and what by that we mean is the variance of x bar as small as possible. And as it turns out, if I write x bar as 1 over n sum of the xi's, the variance of that thing is as small as it can get. It's way smaller, for example, than this one here. Is it sufficient? Does it use all the given information? In this particular case, if we've got n observations, we are making use of all the information. Here we're not. Clearly we have 7 observations, but we're only making use of 3 of them. So that's not sufficient. Then another point estimator is our s squared, and that's a point estimate of the true variance sigma x squared. And it'll turn out that the sx squared with the n-1 denominator here is an unbiased estimator of this variance sigma x squared. We lose 1 degree of freedom because the x bar here is not the true mean. It is an estimate of the true mean. In fact, we end up with a sum of n terms that are not entirely independent. And that loss of 1 degree of freedom is because these things are not entirely independent. And so we can show that the expected value of this thing is in fact equal to this thing. In fact, you'll sometimes see this estimator. I mentioned this this last week. Sometimes, for example, in electrical engineering, they'll use this estimator for the variance, x squared. This is not the same as this one up here because the denominator here is just n. This is a so-called maximum likelihood estimator of sigma x squared. So it's the estimator that gives me the highest likelihood of seeing sigma x squared, but it is actually not. It's not unbiased. It's a little bit biased. We can show that the expected value of this estimator is n minus 1 over n times sigma x squared. So if n is big, like if n is 100, it's only 1% off. But if n is 3, then it's what I get 2/3 here. So then it's a bad estimator, a highly biased estimator. Okay, so those are some of the measures that we could consider when we're thinking about our estimators. But perhaps more importantly is the question about how accurate are these estimators about what they're trying to estimate. And this introduces the idea of confidence intervals. So for example, like I said, if you were told that x bar is equal to 10, you don't really know how accurate that is. Point estimates basically say nothing about accuracy. To provide information about accuracy, we can define two bounds, and I'll call these L and U, such that the probability that the true parameter lies between L and U is equal to some confidence level, and we'll call that confidence level 1 minus alpha. In other words, the two bounds, L and U, are our 1 minus alpha confidence interval. This alpha value we also call our significance level, and we'll see that the word significance crop up more often in the hypothesis testing to come in week 10. Okay, so if we were able to say, for example, that our L and U were 9 to 11 with 95% confidence, then we are saying that the true mean lies somewhere between 9 and 11 with 95% confidence. And what that means is that L and U are going to be obtained from our x bar, from our estimate of x bar, but every time I take another set of observations, x bar changes, so L and U is moving around. So if I take a set of samples, and I call this random sample number 1, I can compute an L and U, and maybe it encloses the true mean. Okay, we're saying that if this is a 95% confidence interval, then it'll enclose the true mean with 95% probability. The next time I take a set of samples, the L and U might be here, and the third time here, but every now and then the L and U will actually miss the true mean. And this will happen with probably 5%. So 5% of the time, our L and U will actually miss the true mean. I note that the true mean is not random. It's a fixed value. We may not know what it is, but it is a fixed value. It's the L and U that are bouncing around because they are centered on x bar. And x bar changes every time I take a new set of observations. So this quantity here is non-random, but the L and U are random. So they're moving around, and we're looking for L and U such that the probability that they do bound the true mean is equal to 1 minus alpha. Here, we'll illustrate this with an example. I'm sure you've heard this statement, the results of this poll are accurate to within 3% 19 times out of 20. And maybe you've wondered what that meant. So I'm asking in this example to express mathematically that statement. So if R is the parameter being estimated, this could be the proportion of a population that's going to vote for a particular party in the next election, for example. And our estimator is R hat, and this is what we get by phoning 1,000 people in the country and asking who they're going to vote. That gives you an estimate of the proportion of people that are going to vote for a particular party. Then this statement, the results of this poll are accurate to within 3%, 19 times out of 20, boils down to this probability statement. The probability that 0.97 R hat, so 3% less than our estimate, is that R lies between 3% less than our estimate and 3% greater than our estimate is equal to 19 out of 20, which is 0.95. Okay, and that this 0.97 R hat is our lower bound, and 1.03 R hat is our upper bound. So in general, the question now arises, how do we find L and U? Let's take a look at the standard normal. We know that this red curve here is our standard normal distribution. It's centered on 0 and has unit variance, or standard deviation, equal to 1. I can imagine that there are 2 points along the horizontal axis, and I'll call this point here Z subscript alpha by 2, and this is the point having area to the right equal to alpha by 2. And because this distribution is symmetric, there's a symmetric point minus Z alpha by 2 on the left-hand side that has area below it also equal to alpha by 2. So the area between these 2 points is 1 minus alpha. If that's the case, well, we're talking about our standard normal, so here's our standard normal here. And we're going to talk about this in terms of x bar. So x bar minus its mean divided by its standard deviation is my Z value. And the probability that capital Z lies between this point and this point must just be the area in between, which is 1 minus alpha. Okay. Now, we were going to have to substitute some stuff in here. Mu x bar, we recall, is just equal to the true mean mu of x. And sigma x bar is just equal to the standard deviation of x divided by square root of n. Okay, so I know what these two things are. Now I can rearrange this thing to solve for mu of x in the middle. So I want mu of x, basically what I want to end up with here is a picture that looks something like this. Mu of x in the middle, and then something over here and something over here. And that something on the left-hand side is our L, and the something on the right-hand side is our U. Okay, so how do we do that? If we take this expression here and reorganize it, so I first of all multiply through by sigma x bar, which is sigma x over root n. I get minus L alpha by 2, sigma x over root n is less than or equal to x bar minus mu x, which is less than or equal to Z alpha by 2, sigma x over root n. And because I've done the same thing on all sides of the inequalities here, it's still equal to 1 minus alpha. Then I subtract through by x bar. I got minus x bar minus this quantity is less than minus mu of x is less than or equal to minus x bar plus this quantity here. And that's still equal to 1 minus alpha. Now I've got a negative sign in the middle. So if I multiply through by minus 1, the inequalities flip directions. But then I flip them end for end, and I see in my final formulation here, I got x bar minus Z alpha by 2 times sigma x over root n is less than or equal to the true mean, which is less than or equal to x bar plus Z alpha by 2 sigma x over root n. And that means this L value is this quantity here, and the U value is this quantity here. And then the probability that L is, that mu of x is between L and U is just 1 minus alpha. So in words, that we are 1 minus alpha confident that the true mean lies in the interval L, U. And I'll often subscript this interval with 1 minus alpha to indicate which confidence level I'm talking about. In other words, LU is equal to x bar plus or minus Z alpha by 2 sigma x over root n. And we're going to see this form show up over and over again in the confidence intervals, and I'll write it in a more general form shortly. But let's maybe just illustrate this with an example. 6.2, let's suppose that at a production plant, 10 pieces of generic paper towel were tested for breaking strength X, and the following measurements in grams were obtained. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 observations, n is equal to 10. And the question is, what is the 95% confidence interval in the true mean? This is an important point to make here, is that confidence intervals are always on the true parameter. So we'll talk about confidence interval on the true mean mu of x. Confidence interval on the true mean differences between two populations, mu x1 minus mu x2. Confidence interval on proportions, p, proportion being probability of success. So p is the true probability of success, and so on and so forth. And they all have the same basic form for the confidence interval. Let's assume for this problem that we know from past experience that the true standard deviation of the paper towel strength is 800 grams. Okay, so this is an important point to make as well. We're assuming in this problem that the true sigma is known. If we didn't know that, then we would have to use the t distribution. But here we're going to use the z distribution. Okay, so we're looking for 95% confidence interval. That means 1 minus alpha is equal to 0.95, which means alpha is equal to 0.05. So that's our significance level, 0.05. And then basically we're going to make use of this as our confidence interval. LU is equal to x bar plus or minus z alpha by 2, sigma x over root n. I've mentioned here this is a realization since we have observations. We have these 10 observations. Those are little x's. We're going to add them up, divide by 10 to get our x bar. And then we're going to figure out what we've got. Sigma x is 800, and we know n is 10. So we'll have everything on the right-hand side once I look up the z alpha by 2. And that z alpha by 2 is the z value on the t distribution table. That's the very last line of the t distribution table, with area to the right of it is in this case, 0.025. And we can see in the t-table that that's 1.960. Okay, so for n equals 10, we get x bar is equal to 1/10 the sum of these quantities up here, 85.77 plus 94.71, and so on and so forth, up to 9065, which should be our last one. And we get a sample mean, or an average of 9,072.2 grams. Now we just have to plug in the numbers. So our LU is the x bar, which is 9072.2, plus or minus z alpha by 2, which is 1.960, times our standard deviation, 800, divided by square root of n, which is square root of 10. I got 9072.2 plus or minus 495.8, and here is my confidence interval, 85.76 to 95.68. And this now gives us a sense of the accuracy of our estimate. 9072 is basically plus or minus 500 from the true mean with confidence 95%. Okay, so this is the general form of our confidence intervals. It'll be LU is equal to something plus or minus something times something. And so your job in this week, this part of the course, is just to fill in the somethings. The first something is always going to be the estimate of whatever the confidence interval is on. So we're up here doing a confidence interval on the true mean mu of x. The estimate of mu of x is x bar, so x bar is going to go in here. The second one is either going to be t or z. And the same rules as apply as we've seen before. We're going to use z if it's a test on the mean or means where sigmas are known. And then it's going to be t if it's a test on the means or mean or means where the sigmas are not known. We're also going to see later on that we'll use z all the time for proportions. Okay, but that's because for proportions, which is that probability of success p, is really actually a binomial distributed random variable, but we're going to make the normal approximation of the binomial, and then we'll always use the normal approximation there and assume that this then comes from the standard normal. So basically, here's the rule here. We'll use t if the confidence interval is on mean or differences in means and the sigmas are unknown, and we're going to use z for everything else. Okay, and we'll see later if you're using z for proportions and the approximation is not good, there's ways to tell that that's happening. Okay, so let's illustrate this with another example. Let's suppose we sample 25 iron cores and we're trying to determine an estimate of the mean permeability. So we compute the sample mean, or the average, to be 1 over 25 times the sum of our observations, and suppose that works out to be 960. The units here are Gauss per Oerstad. I'm probably pronouncing that incorrectly, but I've actually never heard of an Oerstad before, so I'm not sure exactly what that is, but I'm sure some of you will. Furthermore, a review of the literature establishes that the variance of the core is to be 225. So this basically means that sigma x squared is known to be 225, and that means we're going to be using, go up to our rule here, if they're unknown we're going to use t, but if they're known we're going to use z, so we're using z here. So true variance is 225, that means the true standard deviation is 15. And since this is known, then we're going to be using z alpha by 2 in our confidence interval. At 95% confidence, which is what we're asking for here, alpha is equal to 1 minus 0.95, which is 0.05. And if we look at the last line of the t distribution table, we saw this earlier, Z of alpha by 2 is Z of 0.025, which is 1.960. And now I think we just fill in the numbers. LU is x bar plus or minus Z alpha by 2 sigma x over root n. We stick in 960 plus or minus Z alpha by 2, which is 1.96, times the standard deviation, which is 15, divided by the number of samples, which is 25. And I get a confidence interval of 954.1 to 965.9. So our statement now is that we are 95% confident that the true mean mu of x lies between 954.1 and 965.9. This is not a huge interval, so it means that our estimator is actually pretty good. We could ask what our 99% confidence interval is. If we're looking at 99% confidence interval, then alpha is 1 minus 0.99, which is now 0.01, and Z alpha by 2 becomes Z of 0.005. So this is farther out to the right in the Z standard normal. So it's got less area right of Z 0.005, and so that value is 2.576, and this comes again from the last line of the t distribution. Okay, now then I plug in my numbers again. My mean is still 960. The only thing that's changed here is the Z alpha by 2 value. So I now get 960 plus or minus 7.73, 952.3 to 967.7. And so we see that this interval here is now wider than this interval. It's increased by about 2. Okay. In other words, the higher the desired confidence, the wider the interval, and that kind of makes sense. If you have a wider interval, then you're more confident that that the true mean lies within that interval. We could ask, what is their 100% confidence interval? I don't know if you want to think about that. What interval would we have to have in order to be 100% confident that our true mean lies somewhere inside that interval? Well, you'd think intuitively what that interval would be. It's going to be minus infinity to plus infinity. If you have that as your interval, you know for sure that the true mean lies somewhere inside there. So this is a restatement of that fact. To be absolutely certain the true mean lies within our confidence interval, the interval must be absolutely wide. So basically we're looking now for LU is x bar plus or minus Z alpha by 2, but alpha is 1 minus 1, so alpha is 0. So this is Z of 0, so it's the point Z with 0 area to the right. Well, we know that that has to be off to infinity, okay? So this value becomes infinity. I get x plus or minus infinity times something, gives me minus infinity to plus infinity. So basically, if your alpha value is if your confidence value is too large, the confidence interval is not very useful. It boils down to being infinitely wide, which doesn't really tell you how accurate your results are. So you don't want to choose the confidence interval to be 100%. You want to choose it close-ish to 100%, but usually 95 to 99%. Maybe I should say 90 to 99% are the usual values that we choose for our confidence intervals. Okay, so one of the things that comes out of this confidence, where's our general form here? Let's go back up to this one. Here. This LU is centered on x bar. And so this part of it here is the distance down to L and the distance up to U. And so we could think of this quantity here as being the air around x bar at that certain confidence level. And we can use that to actually figure out how many samples do I have to take in order to achieve a certain accuracy in my estimate. So this is a restatement of this. So we're looking now at required sample size. So at 1 minus alpha confidence, our maximum error between x bar and the true mean mu of x is just half the interval width. Okay, so my x bar is in the middle here. The max I'm 1 minus alpha confident that the true mean lies between L and U. That means at that confidence, the farthest that mu of x can lie from x bar is just the distance between L and X bar, or equivalently the distance between X bar and U. They're both the same. They're both equal to this quantity here. So if I say that I want the error on my estimate to be less than this half distance with confidence 1 minus alpha, all I have to do is set E equal to this half distance. And so I set E equal to this half distance, and now I just solve for N. Okay, so where is it? Specify. So if we specify what E is, and then we solve for N, we get this expression here. Okay, so N is equal to Z alpha by 2, the standard deviation of X divided by the error that we're interested in achieving. We note that we square this, so the error is small, then we tend to get a lot of samples required. Here's an example. Referring back to example 6.3, which was about our iron cores, the question is how many cores would have to be sampled to ensure that the estimated mean permeability was accurate to within 2 Gauss per Oersted 19 times out of 20. Well, 19 times out of 20 is just our 95% confidence. So this is 95% confidence. That means alpha is equal to 0.05. We're given a maximum error here of E equal to 2. So we're going to basically say that that 2 must be equal to the half interval size, Z alpha by 2 sigma X over root N, and then solve this for N. I think we've got everything we need here. Alpha is 0.05, so Z alpha by 2 is Z 0.025, which we know is 1.960. Sigma X is 15. Our error bound is 2. Plug it all in here squared, and I get 216.1. So here we round up, because if we want 95% confidence, if we round down, we don't quite get 95% confidence. So we're going to round up. We need 117 samples, and we get slightly bigger than 95% confidence. Okay. Okay, so back now to confidence intervals again, and looking again at this general form. As I mentioned, this quantity, we got something plus or minus something times something. This one here is going to be the estimator. This is going to be either Z or T, and this is going to be the standard deviation of whatever goes in here. So take a look at what goes in here. If this is X bar, this will be the standard deviation of X bar. And it could be an estimate of the standard deviation, so S of X bar, or it can be the true standard deviation, so sigma of X bar. And basically, I always just remember this form, and then I just figure out what goes in each of these things. And usually it's the thing that's going in here that's the hardest to compute. This one is usually pretty simple. This is just our estimator, X bar, or X bar 1 minus X bar 2. It could be P hat, or P hat 1 minus P hat 2. We'll see examples of those as we go along. This one is a choice between T and Z, follows the same rules as we had before. We use T if we're talking about estimators on the mean or differences in mean where sigma is unknown, and Z for everything else. And then standard deviation, if this is X bar 1 minus X bar 2, we have a little bit of work to do to figure out what this thing is, but it's just busy work and we should be able to do it. Okay, so as I mentioned, there's a whole pile of different confidence intervals that we're going to make that all make use of this standard form. There's a confidence interval on mu of X, which is estimated by X bar. Confidence interval on the differences in means between two populations, mu x1 minus mu x2, and this will be estimated by X bar 1 minus X bar 2. So basically in the third one, we're going to have the standard deviation of X bar 1 minus X bar 2. We're going to look at the same form for proportions. So confidence interval on proportions, which are probabilities of successes, and these are going to be estimated by p hat, and I'll show you how to do that in a little bit. And then we'll also look at confidence intervals on differences between proportions, and this will be estimated by p hat 1 minus p hat 2. Okay, so I mentioned deciding between Z and T. We've seen this rule before. Basically use T if sigmas are unknown and we're talking about confidence interval on the mean or differences in mean. Z for everything else, including proportions. Even though proportions are not truly normally distributed, we use the normal approximation to the binomial. So far we've just been talking about two-sided confidence intervals. We can also have one-sided confidence intervals. So although usually we're interested in the two-sided, sometimes the lower or upper bound may be all that we really need for a problem. We'll see more of this in hypothesis tests because often We're just interested in whether the mean is above or below some value rather than between two values. So we can have a lower bound confidence interval L. So this will be the value of L with where the probability that the mean is above L is 1 minus alpha. Okay, so that value L there is x bar minus z alpha sigma x over root n. This is, we had for the two-sided, it was x bar plus or minus z alpha by 2 sigma x over root n. The L was the minus 1, but it was alpha by 2. So the big difference with one-sided confidence intervals is that instead of z alpha by 2, we have z alpha now. Okay, so L is this one, and U is x bar plus z alpha sigma x over root n. So the one-sided confidence intervals just use alpha rather than alpha by 2, and that's so that we get area above here of 1 minus alpha, or area below U here of 1 minus alpha. In general, our one-sided confidence intervals have the same form, except instead of plus or minus here, we just have minus or plus, and instead of z alpha by 2 or t alpha by 2 here, we have z alpha or t alpha. And then same rules about the use of t or alpha. If sigmas are unknown and we're talking about mu's, then we use t and z for everything else. Okay, that's it for lecture 1 of week 9. Next lecture we'll look at some more confidence interval stuff. Okay, thank you. See you later.